Hi everybody, this is the presentation of our water leakage system. The system is designed in order to monitor water usage in an irrigation system and also to detect possible water leakages through irrigation pipes. Furthermore, our focus is not only to detect possible water leakages, but also to quantify and locate them, so to know precise location of the leakage and how much water has been leaking. So, the main problem addressed is water waste in irrigation system. Our focus on irrigation, so agriculture, is motivated by the fact that this sector is the most water demanding one, with 40% of total water usage per year in Europe, and in the case of Italy, 55% of total water usage reserved for this sector. Focusing on Italy, if we consider that the difference between consumed water per year, that is over 26 billion of cubic meters, and the effective withdrawal of water per year that exceeds 33 billion of cubic meters, we notice that there is a huge waste of water. A fraction of this waste is related to agriculture. However, today existing approaches are more focusing on designing different irrigation strategies rather than caring about effective water leakages through pipes. Instead, we decided to focus on this aspect. Main hardware components of our system are MCU, so a microcontroller unit, that in our case is an ESP32, more precisely LTEC ESP32 LoRa version 2. Then we have a buzzer and a LED used for the alarming system, and a water flow sensor. Obviously, there is also the cloud architecture. And as you can see, we designed the system with a tree architecture because it is a scalable architecture, and we can distinguish mainly three components. There are the sheaf, fork, and branch. The sheaf component, we have a microcontroller unit that is attached to a LED buzzer and the water flow sensor, and it is at the water source site, and so it has to monitor the water flow at the source. Then we have another MCU that is the fork component that is connected to a water flow sensor for each deramation, and finally we have another MCU that is connected to a single water flow sensor and is placed at the irrigation valve site. So as we can see in network architecture, these three main components can communicate between themselves using the LoRa protocol and also with the LoRa gateway. And a main difference is that the sheaf component is attached to a power cord, because ideally it is near some farmer's building, while the other two components, so branch and so fork and branch, are battery powered. So these components communicate between themselves and with the gateway with LoRa, and from LoRa gateway messages are sent to the cloud through MQTT. And the cloud infrastructure is an AWS infrastructure, and we also provided a proper dashboard using AWS tools.
In this part of the presentation video, we will focus on algorithms and software components. First of all, we are questioning about how to detect a leakage. Our first try was leakage detection on a single pipe, the most simpler. So by putting the water flow sensor at the extremity of the pipe, we can compute the difference of water flow and check if there is a leakage. If a leakage occurs, we expect that water flow at the end of the pipe is smaller than the water flow at the start. Our first attempt to detect leakages in a distributed infrastructure is the following. By putting a water flow sensor before the fork, we can correctly detect a leakage by computing the difference between the fork water flow and the sum of the branch water flows. But it is not enough to satisfy the requirements, since we cannot detect which pipe is leaking, as in the picture. You can see the same water flow in both cases, but different pipes are leaking. So our proposed solution is to put two water flow sensors instead of one at the fork site. Indeed, in this case, we can detect also the pipe which has leak. To make the physical experiments, we build this prototype, composed by two water flow sensors and a valve in the middle, to simulate a leakage. Following from the discussion on how to detect a leakage, we have implemented this algorithm. The node near the source sends water flow value to its children, if any. The child computes the value of the water flow by summing the values of its sensors. Child compares received value with its own value. Then, in case of leakage, child sends an alert to the cloud. To avoid false positive in the leakage detection, we have tried three different algorithms for synchronized test between two different nodes. The three algorithms are the following: the arc, the handshake, and the sync-hack. Finally, we build a simulation infrastructure on IoT Lab to provide a large-scale irrigation water leakage system and to test distributed interaction between nodes. Also, we will use this simulation to make some experiment on energy consumption using the IoT Lab monitoring tools. The nodes communicate with each other using Riot Semtech radio drivers implementation, sending asynchronous messages containing the water flow value. Each node also sends leakage message to the Things network using Riot adaptation of the Semtech LoRa32 implementation.
Hi, and now we are in the evaluation part. In this part we will see the energy consumption and the setting of the threshold in the system. We have done some algorithm analysis and we have found that the water flow before the source is not constant, so the ACK algorithm is not accurate enough. In fact, we can see that here between the source and the sun the values are really different. We have done the same tests for the handshake and the sync, and we have found that this algorithm does not suffer of the problem. We have done also some analysis on the time of the algorithm, and we have found that there is some difference between the flow between the two flow sensor in a no-leakage situation. Indeed, one sensor works better than the other ones. We have done that some analysis for the time of the algorithm, and we observed that for 0.180 seconds some water is not tested both by source and the node. So this means that there is not a perfect synchronization. With a 10 seconds of sampling, there is 1.8% of influence, and so 0.54 liter per minute of error rate in the sync-hack algorithm. We have done the same analysis for the handshake algorithm, and we have found that there is a similar error. After this analysis about the algorithm error, in particular about the time error, we have analyzed the error of the turbine, so the instrumental error. Because we have not the error of a single turbine, we have observed the error of the two turbines together. And about this, we have observed that the error is not depending on the sampling time, like before on the algorithm error, but only by the augmenting of the water flow rate. Indeed, we have observed that there is an increase of error when there is an increase of the water flow rate. And this analysis can be seen in the sliding window graph, and this is true for the 3 second, 5 second, and also 9 second of sampling. In general, looking at this graph, we have observed that theoretically 5% of error can be good for the threshold, but after we have understood that we have to sum also the error, the algorithm error, and we have decided to put a threshold to 10%. And this threshold works fine and does not have too many false positives. After this analysis regarding setting the threshold, we have analyzed the duty cycle and in particular the energy consumption. We have tried to minimize the consumption. To do this, we have taken different data on the IoT lab. In particular, we have taken the energy of the sending, of the sleep, and of the listening. With this data, we have created a minimization function. We have found that the correct number or message is 828, and these are the messages that minimize the consumption. We have found that the contributor of the sleep is too high, and so we have found in the datasheet of the health tech a lower sleep, in particular the deep sleep. So with this we have found a lower value of energy, in particular 42 watt-hour. After that, we have used another approach. This other approach is called drift rate clock. So we have synchronized the two boards and we have used the same deep sleep. With this, we have found a similar energy. After this, we have found another datasheet with the ESP32 series, and here the energy is 7.78 watt-hour. This is perfect, but we have to see what is your case and your board. After this, we have done another analysis, in particular about the energy of the harvesting of the energy, and we have found that with a microgenerator we will have enough energy for our boards. In the end, we can see different graphs about the energy, and in particular, if you want to understand them, go on GitHub and see our documentation. In the end, in the concept at hand, we can see possible improvements and the future of our project. We can do different things, for example, fixing the LoRa32 library on IoT Lab, take the simulation code and put in a real board, adding buzzer and LED, and solve the problem of the payload in IoT Lab. This is all. Thanks for the attention and enjoy. Bye.